Thank you. Thank you. So thanks for having me. This is my first, I went to New Jersey, but aside from that, this is my first academic trip since, you know. So if I seem at all awkward or anything like that, it's because I've forgotten how to talk in front of people. So forgive me in advance. So I want to talk today about trouble with Hubble. And it's a topic that I've been spending time thinking about. And to be fair, the material that's covered in it spans a huge range of different topics, each one of which would be a subject of a colloquium in itself. So my goal today is to kind of give you an overview of the situation as perceived by a theorist, which is me, and what kinds of theoretical ideas are coming about and what our hopes are to look for them. And I'm also trying new to do this in this fancy way, and so we'll see how that goes. So these days, when we talk about particle physics and cosmology, it's requisite upon us because the snow mass process is going on. We have to put these sorts of slides up and say that as we're thinking about new ideas and new physics, there are various frontiers that we are pushing on. There's the cosmic frontier, looking at very large distances in the universe. There's the energy frontier, pushing to ever higher and higher energies. And the intensity frontier, looking at more and more weakly interacting particles. And there's a synergy between these things. So for instance, you can produce high-energy particles at a collider that might have been relevant for the universe in its early situations. Weakly coupled particles, even though they might be hard for us to produce in a collider or an experiment, can be produced over very long periods of time and can be relevant for cosmology. And for instance, in the energy frontier and the intensity frontier, you might say have very weakly interacting particles that leave displaced tracks or other sorts of signals at those things. So there's these well-established synergies between these different frontiers, and I didn't come up with them, and there are more than I'm listing here. But the point is that there's many different directions that people are pushing in particle physics, and they have intimate connections to each other, so that making progress on any one of them is making progress on all of them, really. There's another way to kind of think things apart, which is, if you're a theorist, you want to elevate what you do a little bit, which is that there's not just an experimental frontier, but a theory frontier. And so as we push forward in all these new experimental directions, we simultaneously have to push forward in our theoretical ideas. And there's also a synergy and interplay between these two directions. And so, for instance, models, you might come up with new ideas, and even if those models themselves may have nothing to do with the universe, they might suggest to you new analyses or new experiments that you can go out and perform that might actually have something to do with the universe. And data informs models because, well, of course, they can provide you signals that you need to explain. There can be results that you actually need a model to explain. But you can also look at the upcoming experiments or the ongoing experiments and try to think a little bit outside of the box and say, well, what sorts of models that have not yet been written down could be constrained by these experiments? Because these experiments give us a tremendous amount of information, and it's upon us to really utilize that and extract the best sorts of information. So in case you fall asleep or have to go, this is my conclusion. My conclusion is that we are in an era of precision cosmology, and that is allowing us to ask and answer questions that we maybe couldn't even necessarily think about asking previously. And one of those questions, namely, how fast is the universe currently expanding, has led to a disagreement between different observations. And a resolution might indicate physics beyond the standard model, which is where I come in, and people like me come in. This is my rough outline. I want to start by going through the expanding universe, talk about what it means to have the universe expanding and the language and terminology that we use to talk about that. I'm going to take an aside, take a step back. That's not necessarily going to be a linear progression to talk about dark forces, dark particles, and how we look for those. And then I'll try to dive into the heart of it, the Hubble tension. So the Hubble tension is a tension between the measurements of the Hubble parameter from two different directions, one using the cosmic microwave background radiation, and one using relatively local supernova that disagree with each other. And I'll try to talk about where those two measurements come from a little bit and how you want to resolve those and the possibility of resolving these things. Before I get into this, let me flash a critical reminder that XQCD provides us, which is that, I don't know where I am on this slide, but if I am on it, you should please let me know if I am on it, because I may not know that I am on it. And if I am assuming that you understand the formula for feldspars, maybe you don't. So please, if I am saying something and I'm using a terminology, because there's a lot of different facts and figures and information in this, and you're like, you never defined that quantity, please tell me that, and I will try and go back and make myself clear. So we are in an era of precision cosmology. You can ask questions about the universe that are not just what's out there, where is it going, but you can ask detailed quantitative questions about what you see out there. It's not just coming from a single data set either. On this slide, you have, for instance, CMB data. You can look at the properties of the cosmic microwave background radiation. You can look at gravitational lensing events. These data are the motions of stars in Gaia. There's also studies of large-scale structure. There's data sources from all sorts of different directions that are giving us information at a very, very accurate degree about the state of the universe, where it is, and where it's going. One of the things that we have seen in the universe, and this, of course, we know for a long time, is that the universe is expanding. And this is encoded in Hubble's law, which is here at the bottom of the slide. But basically, the point is you look out, and you look at a distant galaxy, and you see that it's moving away from us. And then when you look at even more distant galaxies, you see that they are also moving away from us. And the farther away they are, the faster they are receding. And this Hubble's law relationship is just this, that there is a constant of proportionality, which is accurate locally, between how fast things are moving and how far away they are. And this parameter here, h, is what we refer to as the Hubble parameter, that constant of proportionality. So let's take a moment to talk about the Hubble parameter, because it means a lot of things and different things to different people. In particular, to an astronomer, it's the relationship between velocity and distance. That's what we just talked about, right? You go out, you measure how fast something is moving, you know how far away it is. Or see how far away something is, and you can guess how fast it's moving. And that's what an astronomer would tell you the Hubble parameter is. But you can also do some dimensional analysis and see that the Hubble parameter is also a rate. Right? So if you break out this constant, it's got units of velocity per distance. Right? And velocity per distance is distance divided by time divided by distance. So it's really a 1 over time. So that means that there's a time scale or a rate, which is in the Hubble constant. And that rate, or that time scale, is about 14 billion years, roughly speaking. And so you can ask the question, well, what is this rate? What is the physical meaning of this number? And one way to think about it is to ask this question, well, let's imagine that I have an object which is a distance d away from me, and it's moving at a velocity v. Well, how long did it take to get from me to where it is? Well, it's just the ratio of v divided by v, which is h inverse. So if I see a galaxy, and I see how fast it's moving from me, h inverse is basically how long it would have taken to get from me to there. So you can think about this as basically the age of the universe. If the universe were expanding, that's how long it would take for that galaxy to get there. Or if I ran the clock backwards, that's how long it would take for that galaxy to run into me. So you can think of it as roughly the age of the universe, or you can think of it as the time scale over which the universe changes by an order 1 quantity. So this is how long it would take for that galaxy to basically double its distance from me as well. So this is sort of a time scale which characterizes how long the universe has been around and how long it takes for the universe to change. It also gives you a distance scale. Because we have a time scale, and I work in units where c equals h bar equals 1, energies and time scales and distances are all the same to me. But in particular, you can think about this as if there's h inverse, which is how long the universe has been around. Then the speed of light times h inverse is how far a light signal could have traveled over the course of the age of the universe, neglecting things like the expansion of the universe and things like this. But very, very, very parametrically here, these are the ways you can think about the Hubble parameter. It is a constant of proportionality, or a parameter of proportionality, because it's not a constant, as we'll see. It is a time scale of how long the universe has been around. And it is a distance scale of how far information can propagate between the history of the universe and now. Okay? And these different ways of thinking about the Hubble parameter are going to be important. So the universe is expanding. And it's important to recognize that it's not just something that you look out and see that things are moving away. But it's really that the universe is actually moving. Everything in the universe is moving away from everything else. So we think of it, the universe is not just expanding, but stretching. So the way I like to think about this, because I'm not a great artist, is I imagine a grid of galaxies. Okay, so you put galaxies on a grid, and then you say, what happens as you run the clock forward in the universe? And you see that that grid simply stretches out. Okay? Everything moves farther apart from everything else. So if you started off, say, living on this galaxy here, so you lived here, then you look around you and you see that the galaxies have moved away from you. Every galaxy you see has moved away from you. But that's true if you also live on, say, this galaxy or this galaxy. Wherever you live, when you look out, all the galaxies around you have moved away from you. So there's no central point in this universe. It's just that as the universe stretches out in all directions, every single thing becomes farther away from every single other thing, unless they're gravitationally held together to begin with, like a galaxy. You can then run that clock backwards and say, then in the early universe, I squish everything together. When I squish everything together, then everything eventually gets compressed to the point where you don't have any galaxies or stars, anything. You just have a very, very hot plasma. And so if we look far enough back in time, we can see the era where the universe had no galaxies, but instead only had this hot, dense plasma. So an important consequence of this stretching of the universe is that if everything stretches, one of the things that stretches are photons. So photons, if you emit a photon at some point in the universe, it has a color. It has a frequency. It has a wavelength. But if it has a wavelength, and as the universe expands, that wavelength gets stretched, that photon should change its color as well. So you start with, say, a green photon, and then as the universe expands, it gets stretched out, and it becomes a red photon. And it turns out that this phenomenon, which we refer to as redshift, or Z, is the same thing that we talked about in Hubble's law. In one frame of reference, you can think of the galaxy as moving away from you, and so it released a photon. It is moved, has a source which is receding from you, so the photon is redshifted. Or you can say, well, the photon was emitted at some point in the history of the universe, and between then and now, the universe expanded, and in that expansion, the redshift, the photon's wavelength, got stretched out as well. These are different ways of talking about the same phenomenon, and this way is usually a handier way to think about it, because this is some way you can take back into the early universe in a way that it's hard to take the Hubble's law way of talking about it back into the universe. But so the critical point is that photons are redshifted. A photon that is emitted will have its wavelength stretched out. And so if I want to talk about a different point in the history of the universe, I can use this quantity Z to talk about it. So Z equals 0, where the photon is not redshifted at all, is today. So a photon emitted today has the same wavelength as when it was produced. But a photon emitted a long time ago has been stretched out by quite a bit. And so I would say Z is 1,000, means that it was emitted a long time ago. Or Z is 1,000,000. It was emitted a very, very long time ago. So you can use this quantity Z to talk about where in the history of the universe you are. So as the universe is expanding, and as these photons are stretching out, it is also diluting. So if in the earlier time everything was closer together and things expand, then you can talk about the mean density of the universe, and you can talk about how that mean density is changing. So I remember this slide, yeah. So the way you do this in your mind is you go out into the universe and you draw a big box, okay? A big box around a lot of stuff. And that box has to be pretty big so that you can average over the universe, because the universe is very inhomogeneous. There's galaxies and galaxy clusters and you. So there are inhomogeneities you need to worry about. So you need to draw a very big box, something like 10 megaparsecs across or so. So you draw a box which is 10 megaparsecs across, and it's got some volume, 10 megaparsecs times 10 megaparsecs times 10 megaparsecs. That's its volume. And then you can add up all the energy that's in that box. The matter equals mc squared. The photon energy is equals hf. Any other energy like dark energy. But you add up all that energy, and you divide by the volume, and that is rho. Okay? Rho is the energy density, the mean energy density of the universe. And as the universe expands, as that box gets bigger, the amount of stuff in that box is not really increasing. It's staying, for instance, for matter, it's staying the same. So the overall energy density of the universe is actually going down as the universe dilutes. If you think about that box, it has the same number of galaxies in it, but the box has gotten a lot bigger. So the numerator will have stayed approximately the same, and the denominator will have gotten a lot bigger. So the energy density of the universe is falling off with time. This is very, very important. This is important because one thing we know from general relativity is a relationship between how fast the universe is expanding and the amount of stuff that is inside of it. I'm neglecting something of curvature of the universe here because we seem to believe that curvature is very, very small. So for the purposes of this talk, this is the equation we need to worry about. And it's basically a statement which is that h squared, this question of how fast the universe is expanding, is given by 4 pi g Newton over 3 times rho, where rho is the mean energy density of the universe. So you know, or you measure how fast the universe is expanding, you know how much stuff is in the universe. Or you tell me with a theory how much stuff is in the universe, and I will tell you how fast it's expanding. Right? They're the same information content. And so if you have a very, very good model that you believe that tells you how much stuff there is and how that stuff is changing, then you can go back and you can tell me what the Hubble parameter was at any point in the history of the universe. And we do have such a model. Right? We have precision cosmology. We've gone out, we've looked out there, and we've come to understand that the universe can be described by a very simple model full of with very few parameters in it that can explain the phenomena that we observe. And so this is the other requisite plot that you have to show in any talk like this, which is when you ask yourself, well, what is out there in the universe? What is its energy budget? It's this. We see that we have a dark energy component, energy associated with space, which does not appear to dilute. We have baryons, about 5%, and dark matter, about 26%, which is just stuff which, as the universe expands, dilutes. And then we have photons and neutrinos. Neutrinos are their own thing. At early times, they were radiation, so they're relativistic particles. Now they're not. And photons, which continue to be relativistic particles. And since we know how these things behave, photons, for instance, dilute and redshift. Dark matter just dilutes. Dark energy doesn't dilute. You have a model. You can go back and you can tell me the answer to the question, or I can tell you the answer to the question, what is the Hubble parameter at any point in the history of the universe in this model? It's not hard. This is something that just requires algebra and knowing what these parameters are today. Now, an important point is that radiation and matter evolve differently. So if you imagine you have this box of stuff with some length side L here, which previously was 10 megaparsecs, and you run the clock forward into a bigger box beside L prime, well, matter falls off like 1 over L cubed. The energy density in matter falls like 1 over L cubed. The same amount of stuff, bigger box, means that you just scale it by the different box size, right? If I was 10 kilograms over a cubic meter before, and now I'm 10 kilograms divided by 10 cubic meters, right? So I'm just changing the denominator of that. Radiation is a little bit different, because if I have a box with, say, 1,000 photons in it, and my box gets bigger, well, I still have 1,000 photons divided by volume, but each individual photon is stretched out and so has less energy than it had before. So the energy density in radiation falls off faster than the energy density in matter. So matter tends to be important later in the universe, and radiation tends to be important earlier in the universe. Because if you run the clock backwards, the radiation increases and matter increases more slowly. So in the early universe, most of the energy density was in the form of radiation. So you go back to this picture here, and this is the one everybody likes to point to and say, look at this, like dark matter, it's 26%, dark energy is 68%. We have to understand it because otherwise it's a really big pie and we only understand a very small sliver. And you try to justify why we should have big research budgets on the basis of the proportionality of the pie that it occupies. But if you run the clock backwards, it doesn't actually look like that, right? If you run the clock backwards, it's a very, very different picture. In the early universe, say at z of 30,000, so this is back even before the era of the CMB. Photons are the majority, 68%. Baryons are 2%, dark matter 11%. Dark energy is basically nothing. Who cares? And neutrinos are 17.9%. They're the second most important thing after photons, even at z of 30,000, which is a relatively recent point in sort of cosmic history. And it's important now, the point I want to make is that we need to be a little agnostic about those neutrinos, because even though theory tells us they should be there, and even though we can see that there is this additional radiation component, we don't actually know that it's neutrinos. Okay? We just know that neutrinos should be there, and we know that and we know that there's radiation there, and so it's natural to make that identification. So let's set that aside here. And now let me do an aside on looking for dark particles. Okay? Right now, I would say, is an excellent time for us to look for dark particles. Okay? Why? Well, take a moment and think about the process of hunting for the dark universe. You have some scientists. They are made out of baryons. Okay? And then you have dark matter. Now, dark matter is not like ordinary matter. It is, in some sense, removed from us by some distance. When it tries to communicate with us, it's strangely muffled, as though we cannot totally understand what it's saying. And it turns out that in many models of dark matter, it can't even directly contact us. It has to use some additional messenger medium to talk to us. So you should not think of dark matter as dark matter. You should think of it as not DM, but SDM. This is socially distant matter. And what better time do we have where our brains are set up to think about that than today, right? It makes sense. Who wants to hang out with anybody? Right? But no, in addition to that, this is a very special time, okay? We have now just come through an era where we've gone through totally unprecedented changes in our understanding of different wavelengths and messengers. So gamma rays had Egret, an early gamma ray satellite that then had Fermi come after it that took it to a level of maturity where we now have this incredibly sophisticated gamma ray map of the sky. Our understanding of the charged particles of the universe had Pamela, which has now been has followed up with AMS, which gives us a credible map of the cosmic rays that are coming through the galaxy. Our understanding of the microwave of the universe, we had WMAP, which has then been superseded by Planck, which has a now all-sky map of what the universe looks like in microwaves. And then in terms of direct detection, looking for dark matter, we had the good, but relatively less, expansive experiments like CDMS, Xenon, and Lux that have begat LZ and Xenon NT. And Rick and I were just telling me, and he actually told me exactly what LZ sees, but I can't tell you. I'm kidding. He wouldn't say anything. But we're entering into this new era of surveys. So we had SESS and BOSS, for instance, and we'll have Rubin. We had Hipparcos, and now we'll have Gaia, looking at the motions of stars. We had SPT and ACT, and now we're going to have things like the Simons Observatory. And technology we have new gravity waves, new radio waves, and new approaches to new types of models. So we're entering into an era where we're going to be going through something similar to what we did before, but with a different set of technologies and a different set of wavelengths, and thus a different set of questions. And so if you are sort of a student of recent history, you want to look at what we've been doing recently and ask the question, well, what of that can we see looking forward as we go through this whole thing again, but with different technologies? Essentially, what are we going to be able to ask? Right? That's the question, what can we ask? So let's think then, imagine that there are other particles in the theory of the universe with their own forces and properties. So which is to say, when I say there are other particles, I don't literally necessarily mean there are other particles in this room or out in the universe, but just in the theory of the universe, let's imagine that there are other particles. And you want to understand what their effect could be on us. And one point that I think is really important to emphasize is that particles like to mix. Okay? In quantum mechanics, you start with a state, and that state has a certain set of quantum numbers that describe it. They could be charge, it could be spin, it could be the energy of the state. And then you have a final state. And that final state will have some quantum numbers as well. And one thing we know about quantum mechanics is that if this final state and the initial state have the same quantum numbers, then there's going to be some probability that one will turn into the other. Okay? It just happens. And you can see that in the standard model. For instance, think about quarks. We have 3 generations of quarks, but there's nothing like a fundamental top number, because if you make a top, at the beginning of your experiment, you might end up with a charm or an up, as an example. Neutrinos. There's no such thing as an electron neutrino as a persistent state. You might make something you call an electron neutrino because it's associated with an electron. But you wait a while, and now you have a muon neutrino or a tau neutrino, because there is no such thing as electron number fundamentally, which is conserved in the standard model or in the model that describes nature, depending on how you define the standard model. All neutrinos mix with each other because they have the same quantum numbers. And what's interesting is that the top has a charge. The electron has a charge. Bottom has a charge. So if you want to talk about the dark universe and dark particles, none of those particles are going to be able to mix with hidden sector particles. If there are, in the theory of the universe, other particles out there, none of the charged particles mix with them because, by definition, those particles don't carry charge. And our particles do carry charge, so they are different quantum states, so they cannot mix together. But the neutrino, as far as we can tell, doesn't carry any quantum number aside from its spin. So if there are other dark particles out there, say similar to the neutrino, imagine there's a dark neutrino that has its own dark Z prime boson and things like this, then at some level you would expect the neutrino to mix with that state. And the thing that we see, that we call the neutrino, that massless state that you produce in a detector or in an experiment, that massless state is not necessarily the thing in the standard model, but it would be some combination including some admixture of these other states as well. So you can write this all down in math, and I can do that. I'm a serious person. I can write down Lagrangians. And the point of it is that if this were true, the neutrino would pick up a tiny, tiny charge under a dark gauge force. Okay? This is just a statement that is not saying anything radical or anything fancy, and you can draw whatever diagrams you want to draw. But the point is that any state that has the same quantum number should mix. That's just what happens. So if there are dark states out there, the neutrino should mix with them. And that's relevant because if you think about, say, how neutrinos are in the universe, if they did have a tiny, 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 tiny charge, there would be some process by which neutrinos, for instance, could annihilate and produce dark gauge bosons, totally hidden gauge bosons. And it could have a tiny, 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 tiny coupling to those dark gauge bosons. But what's interesting is the rate, the production rate of those dark gauge bosons would be proportional to the temperature of the universe. And the temperature of the universe is dropping over the course of history, and the Hubble constant is dropping over the course of history. But if you look at them, the Hubble rate is dropping like some line, and the production rate of these new forces would be dropping as some time, but they'd be dropping at different rates. So at some point in the history of the universe, you would actually start making lots and lots of these. When the production rate of these particles was greater than the Hubble rate, that means that you're making more than one of these per Hubble time, which means over the age of the universe, you start making these things copiously, and the universe would become full of them. Now, I'm not going to try to talk about this model in particular. I'm just trying to say this to motivate the fact that neutrinos are special, and we should be very careful by assuming that that neutrino sector out there is just neutrinos, because the fact that neutrinos can mix with the entire dark sector that's out there means that at late times, the universe might change that neutrino radiation density into something very, very different. And it's worth thinking about what that might be and how it might show up. Because we have these data. Right? We have these precision cosmology data. We can ask these questions. Right? It's not simply something that we're doing idly. It's a real question. So, okay, I put all that stuff over here. Now I did this. Now we're going to go back, and we're going to go back to this stuff. We're going to talk about data again. I'm going to start with a disclaimer, which is that whenever you have new data sets, you're going to encounter anomalies. They will happen. Discrepancies, tensions, things like this. And they can come for a lot of different reasons. Right? You can have rare events that were not modeled. It doesn't happen, right, very often, but it happens. You can have unexpected systematic errors. But you can have actual new physics. And I want to point to the fact that, for instance, the solar neutrino anomaly was an example where many, many, many people thought we simply didn't understand astrophysics. Nowadays, the funny thing is, like nowadays, they see people who are, young enough that you don't remember this as an anomaly. You just know that there are neutrinos from the sun and they flavor convert. But there was a long time where people thought, oh, no, nobody understands the sun. That seems very complicated. Why don't we give up? And people kept pushing and pushing and pushing, and it turned out that indeed, neutrinos were behaving in a very, very unexpected way. So these things, and then we incorporate them, and then we're like, oh, yeah, we all knew that. We get used to it. We forget that we were confused for a long time. Same thing happened with the cosmological constant. So these anomalies are useful because they can push us to think. They might be borne out to be new physics, and they might not, but they can help push us into new directions. And so regardless, they are useful. So let me talk about the anomaly in question, which is the Hubble tension. So the CMB, cosmic microwave background, is a snapshot of the universe as it was at a redshift of 1100, about. So that was the point where the universe went from being opaque to being transparent, and the photons from that moment in time traveled freely from then until they end their 13.7 billion year life smacking into one of our detectors. Think about that. You spend 13.7 billion years traversing the universe, get hit into a detector. This CMB, this fluctuations, you see is not uniform. It's inhomogeneous. And those fluctuations can be calculated and measured. And you can ask questions like, you can do a spherical decomposition of this, or essentially a Fourier transformation of this, and ask on what scales or what angular sizes do you see large fluctuations. So you might see more fluctuations at 1 degree and fewer fluctuations at, say, 18 degrees. And this is what's plotted here. This is essentially a measure of how much you see in terms of fluctuations at different angular scales. And you can see that there's this very, very big peak here right around 1 degree, which I'll talk about in a second. But there are many parameters that go into fitting this. The current Hubble expansion rate is one of them in a way that I'll describe. And if you use this to measure that Hubble rate, you find out that it's 67.4 kilometers per second per megaparsec. You can forget about the units, just remember 67. Okay? So how does this measure Hubble? How does the CMB measure Hubble? Well, there's a way that, to me at least, was introduced by Lloyd Knox that is the way I like to think about this, which is this is essentially a horizon problem. A horizon is the statement of how far can you see? How far can a signal travel in the universe over the total history up to that moment? So you can ask the question, well, what is the horizon during the CMB? How far could a signal have traveled before the CMB happened? Because this first peak you see right here is essentially that you had gravitational potentials and stuff was falling into them. But you might have really, really big gravitational potentials, but if the universe hasn't been around long enough, there's not enough time for things to fall into those gravitational potentials to amplify them. So things can only travel a certain distance, and the distance that they can travel in the early universe is however long the universe had been around times the speed of those particles. So what you do, if you're us, this is us. If you're us, here, all right, my pen is not working. It was? Okay. If you're us here, and you look out, there's some feature on the sky. And it's fine. You don't need to necessarily understand the physics of that feature. There's some feature on the sky of a given size. How big does it look at it to us? Well, it's got some physical size, RS, how big that thing was at the time. And then there's how far away it is, D. And the angular size is just the ratio of those two numbers, right? You have a triangle. This angle here is just that number divided by that number. So if you want to know this peak here, what is the location of that peak? Where should it be? You want to know two things. How far away is it from us? And how far could a signal have traveled at that point in the universe? And if you know those two numbers, you take their ratio, and you can figure out where that peak is. So as I said before, the Hubble parameter tells you how long the universe has been around. So how far a signal could have traveled at that moment in the universe is whatever the Hubble parameter was at that time. So you go back in time, you find the Hubble parameter at z of 1100. That tells you how long the universe was around then, and that tells you how far a signal could have traveled. So that's essentially the numerator. And the distance to that surface less scattering, how far away is it? Well, that's based on how old the universe is today. And how old the universe is today is basically the Hubble constant today, Hubble parameter today. So if I want to know where this angular peak is, if I want to know where this first angular peak is, is essentially how old the universe was then divided by how old the universe is now. And yes, there's lots more complications to get at, but basically that's what it comes down to. How old the universe was then divided by how old the universe is now, and that tells you what that peak is. And since those things are both Hubble parameters, this is essentially a statement that if I think that I know all the physics that goes into this Hubble in the early universe, right? I know how many baryons there are, I know how many photons there are, I can go back in time, I know how much energy density was around then, I can calculate the Hubble parameter back then very precisely, I know what the numerator was. So, well, I've now flipped things to take away the inverses. If I know how far away, if I know this parameter, and I measure this, then I can extract the Hubble constant today, right? If the question is, I have a ratio of how long the universe was around then and how long the universe is around now, and I measure that ratio, and I know one of it, then I can figure out the other. And this is how the CMB basically finds out what the H naught is, okay? And it's in essence because, I want to emphasize this, because it is figuring out, you can use the CMB to determine the Hubble parameter, but it's doing it because it thinks that it knows what the Hubble constant was then. The only reason you can use this to figure out this is because we think we know this. And if you don't know this, then you really can't use this at all, okay? If you're wrong about what the Hubble constant was at the CMB, then you can't use this to extract what the Hubble constant is today. And again, there's math. So that's the CMB, right? The CMB is a measurement of how fast the universe is expanding then and how fast it's expanding now. What about other ways to measure the Hubble constant? Well, the most successful program for this has been using supernovae. So supernova measured the Hubble constant using, people measured the Hubble constant using supernova, what are called standard candles. So standard candle is an object of known luminosity. So you find some object whose luminosity you just know intrinsically or you can figure out. And then you measure its apparent brightness. And again, you know its luminosity. You measure its apparent brightness. That tells you its distance. OK, now I know the distance to that object. And then if I measure its redshift, or the redshift of the system that it's in, I now have determined the recession velocity, and I have determined the distance. I have now determined the Hubble parameter. Right? And so this incredible project, this, uses, there are no nearby supernovae to calibrate directly. So it uses Cepheid variable stars, which are things that we can calibrate as ways to measure distances. Those Cepheids then allow us to measure distances to supernova, and then those supernova allow us to go to even farther distances. And so with these calibrated, critically calibrated supernova, you can measure how fast the universe is expanding nearby. And that's been done. And the collaboration that has the biggest data set on this is the SHOES collaboration. And they measure a value of H naught of 73.2, which you can contrast with 67.4. And as it stands right now, you can cut and dice these things in different ways, but the tension is basically 5 sigma. And people will argue a little bit about that, whether it's 4.8 or 5.1, but basically that's right around there, right? So these are two of the more powerful measurements of the Hubble parameter, but there are others. You can use what's called baryon acoustic oscillations, which is a feature that you see in large-scale structure. That also finds a value of something around 67. And then there are a variety of other ways that you can measure the expansion rate. Some of them are calibrating those same supernova, but in a different way. So that, for instance, is this. This is those same supernova, but calibrated differently. But you can also use, for instance, masers or gravitational lensing systems to measure the expansion, the local expansion rate. And what has emerged from these different techniques, again, each of which is its own colloquium, is that if you take the measurements that are basically measurements of what the Hubble constant is based on what you think about the early universe, they tend to agree down here at low values. Whereas ones that attempt to directly measure what the expansion rate is at late times, they tend to have these high values. And so this discrepancy has been pointed out repeatedly now by many people and noted that there really does seem to be some sort of a tension between late and early universe probes. And I will be frank with you and say that if it were just this question of shoes, if there were just shoes, I would still be excited about it. But I would be probably pretty willing to say, yeah, but how well do you understand Cepheid variable calibration of these supernovae? Maybe that's off. They're on some tail of something. There's some evolution something. But the fact that there are other measurements which aren't as powerful but basically agree makes me think that there's possibly something to this. Okay? Certainly enough for me to spend my time on it. So like I was saying, this is basically a horizon problem. Okay? You measure the universe, you measure h0 with, say, the CMB. You're doing that because you think you know how fast the universe was expanding then, and you use that to figure out how fast the universe is expanding now. But if you're wrong about how fast the universe was expanding then, you're wrong about how fast the universe is expanding now, right? If you're wrong about the numerator, then you're going to be wrong about the denominator. And so what you can imagine is that it's possible that what you should think about then is whether or not you can change how fast the universe was expanding then, and that will then allow you to change how you infer the universe is expanding today. Sorry, that's my son trying to call me, probably because he wants iPad time. So this was pointed out as soon as this tension appeared. This was pointed out as a possibility. Okay, so here's a paper from Rees, Adam Rees, who's the leader of the Shoes collaboration, who basically said, okay, well, if you need to change this Hubble parameter here, why don't you just change the energy density of the universe back then? Add some more stuff. If you add some more stuff, then that makes the Hubble constant bigger then. And if you keep the ratio fixed, that changes the Hubble constant now as well. And this is a plot by what they looked at something which they call N effective here, which is the effective number of neutrinos in the universe. So the canonical number is slightly more than 3 for technical reasons about how the universe evolves. But what they find is that if you allow a system to have more neutrinos, it can float up here and explain the data. So they're doing 2 different data sets, one including these supernova priors on h0 and one not including the supernova data on h0. And they found that adding neutrinos could explain this, and thus possibly our mistake is assuming that we understood what was going on in those neutrinos back then. But people have looked at this, and people have found that if you add neutrinos, it doesn't just change the expansion rate of the universe. It changes all sorts of things about the CMB. It changes how those bumps and wiggles die off as you go out to higher multiple, to smaller angular scales. And so it's sort of like whack-a-mole, where you push it in one spot to fix the Hubble problem, and it pops out somewhere else in your spectrum of your multipoles. And it turns out, and this is a really wonderful paper by Bernal, Verde, and Rees from 2016. And let me just show you what they do here. So they look at precisely this. They look at this question. And you look at what the values of the Hubble constant you can have using, say, lambda CDM, which is this red one. And then you can expand that theory to include additional neutrinos, and you get this big green band. Okay? So what you should read from this, and then the black band is the h0 value that is measured from Rees. So you should look at that and say, the left-hand plot tells you, aha, the green band overlaps the black band. That tells me that adding neutrinos would allow my theory to envelop and overlap the measurement of the Hubble parameter that I wanted. But as data have gone on, and there have been additional data, for instance, polarization data, so we're not just measuring the amplitude of the fluctuations on the CMB, we're measuring the polarization of the CMB, and you include that data as well, you find out that this agreement goes away, which is what you see over here on this, which is that the green band, which is if you allow yourself to include neutrinos, no longer overlaps really the preferred value of the Hubble value. And this is old data. It's actually gotten worse since then. So if you're a model builder, if you're a theorist, you don't give up, right? You say, it's an opportunity. It's an opportunity to think. So you say, OK, there's a clear tension. You need to add additional stuff during radiation. That's our kind of model building problem. You need to add additional stuff during recombination to change the Hubble rate. But just adding neutrinos is wrong. Okay? It can't be just neutrinos. It has to be something else. And so the next step that people thought about was, well, what if this stuff isn't just neutrinos? What if you're adding stuff that has interactions? Then those neutrinos will bounce off each other. Not neutrinos. These particles will bounce off each other. And as they're bouncing off each other, instead of spreading out and destroying some of these tails, they're kind of confined, and they're not as able to deplete these higher multiple power that you do with neutrinos. And so this was studied. So Kreis, Recede, and Doré, for instance, did a study in 2019 where they found that you could do a pretty good job with a dark fluid to fit the data. But when it comes down to it, it's a pretty good fit, but still worse than about a 3 sigma tension. So it does something for you, but not everything. This is sort of a representation of that, which is not easy to see. But on the left, you see plots where if you don't include shoes in your data, so you just take the CMB data and you do a fit, and you find out that if you don't include the CMB, the value of H naught is low. It actually does not want any additional radiation. And it's only after you include the shoes data that you start wanting additional radiation. So in some sense, the CMB wants one thing, the shoes data want another thing. When you put them together, you can improve the situation, but you're still left with a tension. Okay. How does a particle physicist look at this? Well, I look at this, and I say, I have an interacting fluid. How does an interacting fluid get formed? I have a particle, and I have force. Okay? This particle is floating around, and it bounces off of itself through some force. And the simplest model that I can write down of that is a fermion, psi, and a scalar, phi, and a coupling between them. Right? So fermion floats around, emits a phi, bounces off another fermion. Now I've got lots of phis around, so I've got a fluid full of phis and psis floating around the universe, bouncing off of each other with some strength, which is lambda, which doesn't really matter here. But that's how a particle physicist thinks about this. Right? You say, let's not just talk about fluid with equation state. Let's write down a real model. Let's write down the actual particle physics of this. And it's got 2 particles in it. And if I want this thing to actually do this, if I want this thing to actually be a tightly coupled fluid, that scalar can't just be anything. That scalar actually has to be pretty light. It has to have a mass less than about an MeV. If it's too heavy, it's irrelevant to the process. It's gone from the equation. So you need to have a pretty light scalar field. And something that we know from our years and 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 years of thinking about the hierarchy problem is that scalars want to be heavy. It's very hard for scalar fields to be light. So this scalar field, this phi, should have a mass, and it shouldn't be 0. And if you want to understand it, you need to control that mass. And one natural way to control that mass is to imagine this is some sort of supersymmetric theory, which is not really important, but does give you some essence of where you might expect that mass to appear. And in a supersymmetric theory, you would expect that mass to possibly appear somewhere around the EV scale. So all that is stuff that you can basically ignore, except for the fact that if you have a fluid, there should be a force-carrying particle in it, as well as a scattering particle. If it's a scalar, that scalar should have a mass. And that mass could very reasonably have a mass which is sort of relevant for the CMB. So we did an analysis of this model. And by we, I mean them. And by them, I really mean Melissa. And it turns out that there is an interesting phenomenon that happens in this process. And I'm going to tell you a funny story about it, because I have enough time to tell you the funny story. So imagine you go up to high temperatures. At high temperatures, you've got a fluid. That fluid has phis and psis. Then you cool that fluid down, and eventually the processes are such that if the psis don't have very much energy, it's very hard for 2 psis to produce phis, but 2 phis can produce psis. Okay? So essentially, the heavy particles annihilate into the light particles, but the light particles can't produce the heavy particles anymore because they're too heavy. So you go from a period where you've got both particles at the early times to only one particle at the late time. And this actually happened in the ordinary universe. When we're talking about photons and electrons, in the early universe, you had neutrinos, photons, and electrons, and the electrons and photons were all mixed up, and eventually all the electrons put all their energy into the photons, heating the photons up. And that's actually precisely what happens. you follow your nose, entropy is conserved, and what you find out is that at the end of the day, the psi particles, after you go through this mass threshold, you go through this threshold before which you had 2 particles and after which you only have 1 particle, and you find these psi particles heat up. And they heat up by a very calculable amount. And what's funny, though, is that they heat up, but they heat up by more than enough to just compensate. They actually heat up by enough that actually increases the total energy in that fluid. Okay? Let me explain what I mean here. What I mean is, imagine that you've got N fluid, right, which is the sort of energy density in this fluid compared to a neutrino. At early times, maybe you had something like 0.5. You're cruising along, and then eventually you hit this temperature of the universe where you deplete one of the particles, and it increases, and you end up with about 30% more. So not only does it heat up, it heats up enough that you actually increase the amount of energy that's in this whole other fluid. So a fluid that was maybe less important early becomes more important late. And I did not know this phenomenon. I was actually shown this phenomenon by Asher Berlin, who had studied it previously. And then he was talking to some colleagues of his who are at Fermilab, and they had done a journal club on our paper. And they were like, we don't understand this increasing, because when you do early universe cosmology in grad school, everybody learns this heating up thing. It's like standard thing. Everybody learns this heating up thing because it's in Kolb-Turner. And but nobody, or at least I didn't learn the fact that the whole fluid heats up. And Asher said to me, it's standard stuff. It's all Kolb-Turner. And the person who was talking said, well, Rocky Kolb was in the audience, and he also didn't know what was going on here. So anyway, it was non-trivial. But the point of this whole exercise is to say that if you're a particle physicist, you want to get into the details. And you want to think about the details. And you want to think about the implications of those details. And what I'm saying is that if you think about these fluids, if you're trying to solve this problem, and you think about those fluids naturally have a mass threshold in them. And that mass threshold is naturally in an interesting range and changes how you should do your fits to the CMB. And if you do those fits to the CMB, it has some features. It shifts the peaks in slightly precise ways. You can do big global fits to them, blah, blah, blah. And what do you find? Well, what you find is that the CMB, if you have a step, if you have this sort of transition fluid, you find that the CMB alone, forgetting about any data from the early universe, actually already wants this fluid to exist. So contrast that with radiation, adding neutrinos or adding those other types of radiation. The CMB alone does not want those. It's only adding the shoes data that pulls those things into being interesting. But the CMB alone seems to like a step. Not a lot, but it does like it. And it likes its peak to be a redshift around 30,000. Okay, so this is where this transition should happen, at a redshift of around 30,000. Then you can go back and you can include the shoes data and do the same thing again, and you find that it's still basically consistent. So if you don't include the supernova data, then the CMB alone seems to like this model and want there to be a transition in the dark sector. And when you add the shoes data, the theory very strongly wants to have a step in the dark sector. Okay? There's a huge improvement in the fit compared to the number of degrees of freedom you add to the model. Now, the difference between a story that I tell my kids before I put them to sleep and science is whether we're going to answer the question with data, right? And this, I think, is in that latter category. And in particular, the Atacama Cosmology Telescope, which already has data recorded that have not been put publicly out yet, is going to improve the situation. After that, there will also be the Simons Observatory and CMB Stage 4. But for a similar model, Hill and collaborators last year showed that the upcoming ACT data, which should be public and available sometime next year, can constrain these sorts of models by 20 sigma. So maybe it's lambda CDM, and there's something wrong with the Cepheids or something like that. Or maybe it's not lambda CDM, but it is not a bedtime story. It is science that we're going to know the answer to in the very near future. And so in terms of this particular project, I would say something like this. OK, there's a mild preference in the CMB for this kind of a model, and it wants additional radiation, and that seems to be pretty robust in the data. And then I could get really excited, and I could say, okay, have we solved the Hubble tension? And if, if I were giving a job talk, I would say, yes, we've solved the job talk. But I've already got a job, so I'm not. And I would say the answer to that is it doesn't matter. Okay? And then I would say, okay, it does actually matter. But that's not my point. My point is, we are having a conversation. I admit it's a bit of a one-sided conversation, but a conversation nonetheless, about whether or not there is a mass threshold in a subdominant fraction of the radiation density in the universe 13.7 billion years ago. Okay? And it's an answerable question. Okay? Something we're going to be addressing with data. And so my speculation, and this is why I say let's think about where we've been and where we're going, is that if you think about the sorts of questions we've asked about dark matter. Asked about, is it strongly interacting, self-interacting, is it dissipative, is it warm, is it fuzzy? We went through all this process as the data came in on dark matter, and we started really thinking, taking it seriously, right? Taking it seriously, these questions. What is it? How does it act? Because we could constrain it, right? There were actual data that allowed us to constrain it, so we took it seriously. And what I think is that we're about to enter into a similar period for this dark radiation because we can constrain it, because there will be data, and we can ask these questions. This is not the only model out there. There's a model of neutrino masses called the Myron. There's a model called early dark energy. There's varying electron mass with cosmological constants. There are many, many, many models. Okay? I've taken you through one story arc because it kind of makes sense of evolving. But there are a lot of different ideas out there. But I still think that we've only touched a few of the possible ideas. Okay? So I would say we've made a small step here. We're in an era where cosmology is allowing us to ask detailed questions about the dark sector. Not just dark matter, but about this dark radiation as well. And this dark radiation, like dark matter, is there. And we think it's neutrinos, but we also know that neutrinos are kind of special. They're different. And so we should be very, very careful about our assumptions about things being neutrinos. The fact that we see attention in the data prompts us to think very carefully about this fluid and to understand what happens in it and to understand that even small changes in that fluid can have measurable effects when the data are good enough. And here is a model. Okay? It's a natural model, and the point is that a particle physicist does have some role to play here because as you actually think about what a particle physics model looks like, it can tell you what the cosmological signatures that you should be thinking about might be. And finally, regardless of what ends up holding true, whether it's this model or a different model or anything like that, we are going to be asking very, very, very detailed questions about dark radiation in the near future. And that's very exciting. I think that's an exciting time. So thank you very much. Yeah, so the big... I don't think very painful. That particular thing is not very painful because you can calculate some transfer function and then you can grow that because, the nice thing about all this stuff is it goes away because it all decays the energy density falls off rapidly and so you transition into an ordinary CDM universe anyway. And we understand that very well. So it's really about modifying the place where this thing I think is where a lot of these things is that they actually change the amount of dark matter that you have. And when they change the amount of dark matter you have, that itself has significant impacts on the growth of structure. And so I would say that there's sort of two perspectives you can have on this. This model, as I've described it, doesn't have a very serious impact on this question of there's a separate tension out there called the SA tension about the size of the amplitudes of fluctuations at 8 megaparsecs. And this particular model doesn't have a very big effect on it. But what you could say is that if something like this is going on, some of it's a matter of attitude. If something like this is going on, then I kind of say my attitude is, well, then I would want to take the next step and say, well, what if there are two fluids? Or once something interesting is happening, then why should that be the end of it, right? And so I might want to think maybe dark matter is interacting with these things, or there's a component of dark matter that's interacting with these things, or whatever, right? And that, of course, becomes much, much harder. That becomes much, much harder. right now what we're trying to do is not that, because I don't think that we're going to be able to live or die in this kind of a scenario on late time structure. We're working with Colin Hill, who did the early dark energy. He and his collaborators did the early dark energy analysis on with public ACT data, and so we're working with him to try and use that to see what that says about the situation, and hopefully that will give us a sense of, prepare us for the situation when the next level of ACT data become public, and then we can do that, because that's a very short time scale, in terms of everything else, right? The year is nothing, all things considered, right? Yeah.
Is there any evidence that the universe expands, is it consuming some numerator on energy density?
Is it consuming energy?
Is there consuming some, reducing the numerator of the calculated energy?
You mean like this? This, if we say rho is equal to, say, the dark matter energy plus dark energy plus dark radiation divided by volume. And so we think, right, this we think is constant, basically. This is constant. This, in some sense, grows, because the volume of space in your box gets bigger, so the total amount of dark energy in your box gets bigger. So this part of it stays constant.
When we sum up all the things, then it's constant.
Well, what it looks like, if you look at this energy density, right, it was declining, and then it entered, so this era here would be the dark matter dominated era, when most of the energy density, if you looked at this, most of this energy density was in this. But then as the universe has gotten bigger and bigger and bigger, eventually the dark energy has come to be the dominant term. And so this energy density now looks, it's moving into a period where it's approximately constant. And that's just to say that the energy density today is dominated by dark energy, and dark energy is the density of space. So it doesn't matter how big you make your box. If you have a bigger box, then you have more space. And so the energy density stays the same. But this has now been pretty well measured, by looking just at, you can look at the expansion rate, for instance, the supernova cosmology project, Pantheon, or look at supernova data and can study the expansion. BAO data allow you to study this expansion as a function of redshift. And so this is pretty well mapped out. And it's very well, like in this era, this dark radiation doesn't really matter. And it's just dark matter and dark energy that's relevant.
Talk about the matter density is proportional to 1/L. Radiation is 1/L.
Yeah. So the energy density in radiation is basically if you imagine your box, it's the number of photons, right, times the energy per photon divided by the volume. So as that box expands, the number of photons, being really, really simplistic here, but the number of photons stays the same, okay? But the energy per photon is, because the wavelength is being stretched out, each individual photon is getting less energy as the box expands.
Does it mean it should be some energy density which is proportional to 1/L minus 1/L?
Well, you shouldn't think of it as a sum of densities. You should think of it as a sum of energies divided by volume. And so the dark radiation, or radiation in general, the photons, that dilutes as the universe expands, and this does not. Or the energy in the box, if I have a box with matter in it, the energy from matter in that box doesn't change. But as the box is getting bigger, the energy in each individual photon is getting less. So if I think of this as these two pieces in the early universe, this one is declining as the box expands, and this one is staying the same as the box expands. But you should think of it as a sum of energies, not as a sum of energy densities. Maybe we can talk about this. But yeah, great.
I wonder if you make the dark matter long-lived but a reasonably long-lived, so it slowly decays. If that go in the right direction or not?
Slowly decays meaning decaying today?
No, it started decaying in the early universe, and it was more than
Well, so if you have, so there are a lot of games you can play on this kind of a thing. If you have decaying dark matter, and it's just sort of like straight up conventional, all the dark matter has a lifetime, that lifetime is tau, then basically you have sort of two eras of your universe. One era is shorter than its lifetime, and then it basically is stable. And then you have another era which is longer than its lifetime, and then it's basically gone. And then you have this very brief period in between where it's going from matter to radiation. And that period doesn't last very long in terms of, Hubble times compared to its lifetime. So you can't, for instance, have something decay early on and have it still be around today if that's all the dark matter. If it had a lifetime of, say, 300,000 years, or even a billion years, so if it's a billion years, it doesn't do anything interesting during the
I think it's about the age of the universe, so we just happen to use it.
It turns out, so you can try to do that, but there was actually a paper by Bob Kirshner, which I think kind of is re-saying what Lloyd Knox was saying, where he studied all these sort of late time changes to H naught. Because there's a question, right? I've said, go back to Z of 1100, mess with the universe then. That's what you have to do. And that's what Knox says. And so there's a separate question is, well, could I just like change the late universe, something that's happening now, and fix the problem that way? And it appears the answer to that is, with a few very particular exceptions where you do something very, very pretty radical, the answer to that is no. And that is because you still end up with this basic tension, which is that if you have some measurement of what the Hubble parameter is now, and that's just whatever the distance from here to the surface of last scattering, that's always dominated by what the current Hubble expansion rate is, and that's something that we measure locally. And since most of the age of the universe in some sense happened recently in a log scale, that distance to the surface of last scattering is dominated by a period of time that we can measure directly using supernova and baryon acoustic oscillations. So we can actually measure the Hubble recently and how the Hubble is evolving recently. So it's hard to do a lot of really radical stuff to the late universe. You can do some weird stuff in the intermediate, but then that has its own set of problems.
If you have a celebrity scale or heavy TV, you also have very light gravity.
Yes, you would, yes.
So in our model, what sets the mass of the scalar mediator, and then could that be, say, tweaked to like a sub-EV or very sub-EV mass?
So at one level, that mass is a free parameter. At another level, we know that scalar fields that have interactions want to have masses near the cutoff of the theory. It turns out that a scalar and a fermion together is a supersymmetric theory. That's just a funny fact of life. So it is stable. So I could write that theory down, and if I didn't do anything else to it, its mass would be stable. Okay? It would not get any mass. So in some sense, its mass can be anything. However, we also know from our lives, which is that even in a supersymmetric model, nature would have liked to have given you some mass from somewhere. And that's where this EV estimate came from. Now, if you don't care about that, if you want to say, this supersymmetry is accidental in this model, it's hard for it to be totally accidental because there's a relationship between the couplings, but whatever. Let's suppose supersymmetry is there and there's no gravity-mediated contribution, which, you can, Randall syndrome, blah, blah, blah. We can do all those things. We lived through the 90s. And you can turn off those masses if you want, and you can make it very, very small. But I think probably most of us would say it's hard. Yeah, an interacting non-axion field wants to have a mass. So.
I think we use a scale before to turn off the low L, high L.
Yeah, so that's to get what we talk about. If you think this is relevant for the CMB, the mass scale has to be pure during the CMB era. If it happens well after the CMB era, it just looks like nothing. Yeah.
Could the CMB plasma itself increase the mass?
Maybe if lambda was big enough, but you wouldn't go through this transition then. right? Because the transition, because then your mass would always be proportional to the temperature, and then when you would always stay below the temperature as the temperature cooled off. That would just change the overall scattering rate, so I don't think that would do it for us.
So the signature in the ACT data, is that one in which you're just sort of scaling the higher order, you just scaling it, or is there something actually interesting and printed in there that varies as a function of
the leading effect appears to be, so as I've come to understand with the CMB, it's always a question of what are you holding constant? Because you can always dial these other knobs to do other things, right? So you have to start by saying, when you do this, what's the effect? You always have to say, what are you holding constant? So let me say what I'm holding constant. Let's hold the late universe constant, okay? Let's imagine H naught is constant, and I'm going to talk about a model of strongly interacting radiation. So I want to compare this model to a standard strongly interacting radiation model and ask what's the difference. And so basically, there are modes that came inside the horizon late, and there are modes that came inside the horizon early. And the modes that came inside the horizon early saw a universe with less radiation. And the modes that came inside the horizon late saw a universe with more radiation, relatively speaking. And so what that does, the leading effect of that is to shift if you look at the multipole peaks that came inside the horizon before, they're shifted over. And the ones that come in late have the same location they did before. So that's sort of, you want to get into the nuts and bolts of it, that's the actual effect. And that's the leading order effect. And higher order, again, you're starting to spin knobs and things like that.